Good. Okay. Yeah. Thank you, Levin. It's really fun to be back here at CCA. It's only been a few months. So I'm really excited to tell you today about a new view of time domain astrophysics that's really being driven by a new era of big data. So I hope to convince you that that's true. And in particular, I'm not actually going to show you so many new scientific results, but more so, hopefully, try to convince you that there are ongoing and upcoming really exciting methodology-based problems that will lead to really, really groundbreaking scientific results in the upcoming few years. And so this talk focuses on the union of, well, the intersection of data-driven astrophysics and time domain astrophysics and the problems enabled by these large surveys. Because I was here not too long ago, I very much feel like I'm in the company of friends. And so to answer any questions people may have about how the last few months been going, loosely like this, as junior faculty. So that's been great. But luckily, thanks to a wonderful emerging field of science, I'm still very excited to tell you about the fun science I've been able to do in these last few months. And the months preceding my professorship while I was at CCA. So some of you may see papers of your own. Feel free to pat yourself on the back for those. So let me start my talk by more seriously showing you this slightly low resolution GIF of our night sky evolving before your eyes. And to ground us a little bit, time domain astrophysics, as I realize it, is really about the universe evolving on a human timescale. By that, I mean from hours to years. So whereas cosmologists maybe consider 1 million years to be quite young, and they're correct in the grand scheme of things it is, this is really one of the only places where we can actually see, especially what I think about extragalactic transients, the nucleosynthetic active evolution of our universe. That's what time domain physics is really after. And the probes of this, extragalactic transients, give us the additional benefit of really understanding a number of exciting physics and astrophysical problems. And here I'm just showing my boilerplate examples that I hope you will find interesting. So let's step through them quickly. First, I like to focus on one of the most famous and the most common astrophysical transient, which are type 1a supernovae. They actually show up like candles, really easy to look at. I'm joking. So that's a cartoon representing the fact that they are standardizable candles, which we use to measure the expansion and the change in expansion rate of our cosmos. But more broadly, time domain astrophysics really probes at high energy physics that we cannot reproduce terrestrially. And so as an example of this, we can explore things like tidal disruption events, which is what happens when a star passes too close to a supermassive black hole and the severe tidal forces actually rip it apart. And we can watch that explosion happen in real time, and from it, untangle some of the properties of that black hole that would otherwise be unobservable. It also highlights really interesting late stage stellar astrophysics, especially of massive stars when they've reached kind of the end stages of their lives. So as we know, they will most likely explode as a supernova. But even before that happens, we see really interesting hints at something unique going on. And in particular, I'm showing this real pretty picture of Eta Car, this massive star that we think will go supernova eventually. And during these last few decades or hundreds of years of its life, it's erupting off these large puffs of mass loss that seem, again, to be pointing to some sort of maybe unstable nucleosynthetic process that we don't fully yet understand. And then finally, I'm not going to talk about this a lot during my talk, but some of the newest players on the block involve multi-messenger extragalactic transients. And that means those which have more than one clear observational signal. So whereas most of these guys today, I'll be talking about electromagnetic, the light counterpart signature, the mergers of many compact objects, especially those involving neutron stars, have an additional gravitational wave component that we can quote unquote hear with gravitational wave detectors like LIGO. And in addition to, again, really interesting high energy physics, unique probes of general relativity, they're also telling us a lot about the nucleosynthetic evolution of our cosmos, because these sites are most likely the dominant site for the most heavy elements of our universe, which are known as rapid neutron capture process elements, or R process, things like gold. All of this is to say, there's a zoo of observables out there, and they map into a zoo of interesting physics that happens on these really short time scales. And time domain astrophysics, especially observers like myself, we make our goal to capture these photons in real time, understand what's happened, and understand the implication for much larger systems than the star itself. And I always like to pat myself on the back of my field and highlight the fact now that that time domain astrophysics was really highlighted as a key theme of the 2020 decadal survey, especially due to kind of the upcoming surveys I'm going to tell you about and the staggering rate at which we're going to start finding some really fun discoveries and lots of transients. Let's actually start there. Let's start with numbers. So supernovae are the most common extragalactic transient. So if I say transients, supernovae interchangeably, that's why. And of course, supernovae tell us about the very end of stars' lives, whether that be in a thermonuclear explosion, which is at type 1a, or a core collapse explosion, which is when a massive star dies. And we find these supernovae maybe in pretty surprising numbers today. So here I'm showing you the short history of supernova science, where I'm showing you the discovery rate of supernovae as a function of time starting in the 1980s. And what's fun about this is that we've, as you can see, our discovery rate of these events has been growing at an exponential rate in the last few decades, starting with a few dozen in the 80s to now where we, this is a little out of date, we discover something like 20,000 supernovae every single year. And this is really being driven by wide field untargeted surveys which have come online. Those are surveys that look at large patches of the sky every few nights, not specifically at specific galaxies or anything, just looking for any new points of light on the sky, which are likely to be supernovae. And so that's where we are today. This picture is actually going to really drastically change in the next few years. And that's because a new observatory is going to come online in Chile called the Vera Rubin Observatory. And it's going to start a decade-long survey called the Legacy Survey of Space and Time. And what's unprecedented about this survey is the combination of the depth it can achieve, so how dim those objects it can see, and the area it's looking at. So it will look at the entirety of the southern hemisphere every few nights to a depth that we really have never seen before, 24th magnitude in R band. So it's going to be a supernova discovery machine. And I always like to point out that it's also a huge big data problem. Even if you don't care about supernova science, the data alone will be about an order of 20 terabytes every single night that we have to dig through. But for this talk, we care about LSST as a supernova discovery machine for time domain astrophysics. And I quickly want to mention that I forgot to say this in the beginning, that I am a person who loves questions throughout. Please interrupt me with any questions that you might have at literally any point in time. Go on. Yeah.
The cadence that you report, is with the same filter?
Oh, that's a really good question. And I don't have to repeat the question, right? Everyone can hear it.
You can use your mic. Sorry, my question was if the cadence is with the same filter every 4 days.
Yeah, so that's really, it's again, a good question. So like I kind of stayed up here, there's 6 broadband filters that cover loosely from UV to near IR with LSST. And the cadence I'm reporting here is I'm being pretty fudgy, but any filter being observed, not necessarily the same filter. We will see why that's interesting from a data and statistical perspective in a second. Yeah. Yeah. I can repeat too, if you just want to ask.
So if you go back to the previous point, so there is a peak in like 2005, which is mostly SDSS.
Yeah. So the question was, there's this peak in 2005, is that being driven by SDSS? The answer is yes. I will also note there might be a slight bias in my data because this is how easily I could access the numbers of archival supernovae. For a while, a lot of the supernovae were not quite reported publicly, so it's a little bit harder to get to that information. Yeah. Okay, so let's go back to LSST as our supernova discovery machine. I'm actually going to re-show you the same bar chart, but now with a fun interactive arrow that shows us exactly how much LSST will change the story, where I have changed this to a linear scale, so I am seemingly exaggerating, but not really. This is a game changer for us. So even though our discovery rate of supernovae has been growing roughly exponentially, LSST literally breaks an exponential growth. There will be a 2 orders of magnitude jump in our discovery rate of supernovae from roughly 10,000 to 1 million events every single year. So this is why we really are calling it this new era of big data in time domain. And I have this mysterious black line also now plotted, where I'm showing you specifically supernovae, which are discovered in these surveys that also get just one spectrum. A spectrum is the thing traditionally that time domain astrophysicists use to take our first guess at the underlying physics of what happened. And we all know what spectroscopy is. It's because it's telling us the signatures of the elements that are either being produced in that supernova or that existed within the progenitor star itself. And so these have been essential in the classification of these objects. This is the growth rate of the number of spectra we get for supernovae. So right now, we get spectroscopic classification for about 10% of the 10,000 supernovae we discover every year. And our community throws away 90%. Maybe that's upsetting. I'm okay with it. However, when LSST comes online, the number of spectra we get is not going to increase exponentially. Maybe if we really put resources into this, it'll double. But we're still looking at in the thousands of spectra taken every year, even though we now have 1 million supernovae being discovered. So suddenly we go from a 10% classification rate to a 0.1% classification rate. And now maybe this is unacceptable. We can't throw away 99.9% of our science. And in particular, I like to think of the problems that LSST brings to us, kind of silly, but in terms of having needles in a haystack. The haystack represents, of course, the million or so supernovae or transients that we see every single year, where we may want to be asking problems like, okay, I have a whole pile of quote unquote vanilla type 2 supernovae that are just the death of red supergiants. And I really want to understand, how do the energetics of that death correlate with things like the metallicity, the progenitor star? Those are kind of my haystack questions. Okay, from that haystack, let's be really generous and say that several thousand per year receive spectroscopy. Okay, those will have to be fairly special because a really small fraction will get that. But then from there, maybe only 100 per year are going to actually have quote unquote human hours devoted to their analysis, or even resource limited. Only a few hundred can possibly get multi-wavelength coverage from the radio through the X-ray to fully understand what the photons from that event or what the underlying physics is really doing. So this is a huge problem. This is needles within a needles. And it's such a small number. It's roughly 1 in 10,000 will actually have active follow-up. For an idea of how rare that is, I just told you that we discover roughly 10,000 supernovae let's say in 2021. So that's as if the entire community came together and said, well, we can only write one paper this year. Which object will we choose? That's the philosophical level of importance that we need to start thinking about when we decide which events to actively follow up. It's a really, really tough problem, but it's a fun one. So we'll talk about it. To drive this point home in a different way, I want to point out the fact that the things that we call needles today, as in the most rare astrophysics in time domain that we know about, are very much in the haystack of LSST. Let me give one example. This is a cartoon this is a cartoon representation of a very fun type of supernova that we only recently discovered a few decades ago. It's called a superluminous supernova because we're not so clever in our naming schemes. And these supernovae tend to be brighter than the vanilla types we see. More specifically, they are so bright that we can't possibly explain them with our simple models of the radioactive decay of nickel-56. So we need to have some other energy injection to explain these events. And one of the popular theories is that the supernova kind of gives birth to an extremely highly magnetized, rapidly spinning neutron star. And as that neutron star begins to spin down, it injects some angular momentum into its supernova ejecta, and that provides a little bit extra oomph to the light curve of the supernova that we see. And so with this population of superluminous supernovae, we're probing a really weird and rare set of astrophysics that seems to require exceptionally odd galaxies that are really metal poor and produces magnetars, these highly magnetized neutron stars, that have no real counterpart to the ones that we see in the Milky Way. We only know of about 100 or so of these types of events. And so these are very much when one of them goes off, it's a needle. We stick a lot of multi-wavelength follow-up onto them to fully understand this magnetar business. Okay. In particular, they're about 1% of our observed population. And this is a plot just from a recent paper from the Zwicky Transient facility that gives an observational breakdown of the fraction of different supernova types. It doesn't really matter what their names are. It just represents slightly different astrophysics. And you have to go all the way down the pie to finally get to the superluminous supernovae. They're quite rare. However, if we just do a simple scaling, and we've done a detailed study here, we are able to discover about 10,000 superluminous supernovae every year. And of those, the majority we can in fact study even without observational follow-up. So these guys are not needles by any means. They are the haystack. So if we want to find these 1 in 1 million type of transients, we have to in many ways go deeper and really think about some exotic physics. So not for this talk, but often I include a few slides about, that's mainly just an encouragement to any theorists out there. Now is the time to just kind of send out your wildest theories because it's so helpful if we know what we're looking for. And one such idea, which Matteo also worked on while I was here, is, for example, an exceptionally large explosion of something which produces a black hole with a transient accretion disk can actually produce our process, these rapid neutron capture elements, and it would look unlike anything we've seen. It's very much a 1 in 1 million event. We've never seen it before, but it's something we're sensitive to. So really send out your exotic ideas now so that observers can look for it in the future. Okay, but going back, the key point here is that the questions that are now open to us, thanks to LSST, are unlike anything we've seen before. And here I'm highlighting exciting statistical and data-driven methodologies that have to be developed. Things like, what do we do when we only have a probabilistic guess at the underlying physics? How do I possibly do some hierarchical population study with that? How do I actually try to identify physics that I don't know what I'm looking for, the really unknown unknowns of LSST? And sub-problems like, how do I actually capitalize on the fact that LSST will have really rich images of host galaxies, the neighborhood that these supernovae are being born in addition to their light curves? And the basic problem of how in the world do I even classify these things if I can't use my traditional method of spectroscopy? We're going to focus on that problem for today. It's one of the closest ones to being solved, although knock on wood, it's not quite solved. Classification, or having a first guess at the underlying physics, is just a necessary ingredient to answer any scientific question. And so what I have spent a lot of time on is understanding how exactly to solve this problem. How do I guess the physics without having a spectrum? I want to point out that I've said this before, that they're, of course, classically classified with their spectra. But I want to highlight the fact that this is a strange, as most things are in astronomy, a weird historical hierarchy of actually observational features. So things like, do I see hydrogen in this spectrum or do I not? Which is highly correlated, but it doesn't exactly map onto the underlying physics. So we look for these signatures, and then we try to make a guess. So for example, well, if it has hydrogen, it's probably something that has retained a hydrogen envelope. It's probably a red supergiant. And we have to go deeper and deeper the more exotic that spectra starts to look. However, most of this information is encoded in the light curves, where a light curve is. So we can think of a spectrum as a series of small buckets where I'm collecting lots of photons at different wavelengths, very high resolution. A light curve is simply now taking those buckets and stretching them out, having fewer of them, but still having color information. So the shapes and colors of our light curves that we see still can encode the physics, although at a lower resolution. Unfortunately, they don't look like my cartoon. They look a lot more like this, where this is a type 1a. I know that because we got a spectrum. They have really fun data properties. They tend to be quite sparse. So transients, as their name implies, only last for, let's say, a month. And relative to that month, we might get, it's common to get something from like 5 to 10 points. So relatively sparse given the duration that they last for. They're really noisy, as you can see. And then importantly, they're irregularly sampled, both in time and then, as was pointed out, in which wavelength we're actually sampling from. So I might only have information about the bluer photons at a pretty small slice in time, but I know that there is some physical function that drives all of these filters together. So I'll argue, though, that luckily, pretty simple features of our light curves do directly correlate with physics, and that's really helpful for us. In particular, let me point out the two simplest ones we can think of. How bright this thing is versus roughly how long it lasts. That's a really common observational feature space that we typically build. And in fact, if we do this for a series of, now this is just simple models of the most quote unquote vanilla supernovae, that's those which are being powered by nickel 56. If I allow this vanilla model to kind of vary as much as I can within the bounds of astrophysical sense, I get a fairly small locus of points. The vanilla model, as you can tell by my very exaggerated bounds, is really a small cluster of possibilities. And when we expand our view to all of the different engines which can drive transients, the environment impacts that can affect transients, like having circumstellar material, and the lifestyles, I say, of the stars. By that, I mean things like binary interactions. When I actually include all of that, now the space of observations is much broader. And in fact, I can, if I just, even with a few data points, if I see something that's evolving really quickly and it's really bright, well, I know right away that that's a relativistic event, something like the afterglow of a gamma ray burst. And so even these really simple features really strongly correlate to physics. And so now, finally, our goal is to use machine learning and data-driven methods to actually extract features from LSST light curves and try to classify that underlying physics and maybe do a few other fun things that we've mentioned. As a just incredibly minor aside.
Can I ask a quick question on two slides
Of
ago?
course, yeah.
I just was hoping you could explain what's going on the y-axis. I would expect, I would expect those to be reversed. Why do you plot it in this way where you have the large peak magnitudes towards the bottom of the plot?
Yeah, that's a good question. So the brighter magnitudes are at the top, and this is an old astronomical convention that our magnitudes are the negative log of a flux. So brighter is actually at the top. Yeah, that's a very observational thing to do, basically. Yeah. Okay. So as a small aside, just because I kind of pushed this to the back, there are lots of playgrounds of data that exist to ask some of these questions with. I just have like a smattering here of both real data that maybe are limited in numbers, but at least have all of the true systematics of a real universe, and really fun simulated data that are continually evolving to be as close as we can be to real. Feel free to ask me about that afterwards. But instead, let's dive into some methodology. So we are going to be using a semi-supervised classification method for our light curves. And specifically, we'll use a variational, although I don't say that adjective, recurrent neuron-based autoencoder. And our goal is to explain all of these adjectives that are highlighted so that the reasoning behind all of them makes sense. And hopefully, you see some connections with some of your own time domain problems. In particular, semi-supervised just means that, well, when LSST turns on, I'm not going to get spectroscopy of every single supernova. I just told you that. So I want to be able to, well, use the ones that I do have spectra for in order to build a classifier, but then also be able to tell my deep learning model just in general what supernovae look like, even if I don't know what type they are, just to say, hey, this is what it looks like in general. And so to build this classification method, we use this autoencoder structure for our unsupervised component. An autoencoder, it's a type of neural network, which just means it's a series of vectors with like a very tiny nonlinear function. But the autoencoder's job is to take in a light curve, like this beautiful cartoon, and then spit that light curve back out at me. And so you might be thinking that's kind of silly. If I multiplied my light curve by 1, it would have done a wonderful job, but I wouldn't have learned anything. And so really the responsibility of the autoencoder is to learn a series of free parameters sorted as vectors such that the hundreds of data points I might have in my light curve get condensed into just a few numbers, just a small vector, that can exactly describe that large light curve. A different way I think about this as a physicist is it's exactly like learning a physical model. Like if I wanted to model this traditionally, I would write down an Arnett equation, and I would say, yes, the free parameters are how much mass the progenitor had, what fraction of that mass was nickel 56, and how much energy was in that explosion. So those are 3 numbers in a vector to describe this light curve. My neural network's going to do the exact same thing, but I'm not going to tell it about physics whatsoever. I'm just going to show it lots of examples of supernovae, and it's going to learn its own physical model, which, by the way, is not physical. I'm not going to claim that, which exactly describes the data. That's the autoencoder's job. The autoencoder has a very tiny bell and whistle on it, which is that the little boxes of each vector, which are called neurons, are a special type of neuron that's called a recurrent neuron. That just means that my model is able to actively update every time I observe a new piece of information. And you interact with this all the time. Things like your predictive text is, back in the day at least, it was using recurrent neuron models. And so the way this works is that I receive a few data points. My autoencoder takes that and tries to say, well, let me build a model that would describe the entire light curve. But I only have a little bit of information, so I'm not totally sure. But as I get more information, I can update the parameters of my model to be more and more accurate. Let's watch it in action, because I think that's the easiest way to understand. This is now a real light curve. a real supernova, a type 1a. I had a spectrum, so I know what it is. The points are real data from the Pan-STARRS Medium Deep Survey. That's something that has data properties really similar to LSST, and it's a nice playground for us. It's observed in 4 colors, GRIZ. And the lines actually represent the output model that my autoencoder has learned. And it is, in a sense, conditioning itself on the observations. And so with just one high signal to noise observation, it does a pretty bad job. It has something that looks like kind of funky and doesn't quite get to the right brightness. But what's interesting is that with just a few more observations, just a few days later, the variational, sorry, we're not using the word variational, the autoencoder is able to roughly match the luminosity that I expect a type 1a to be as an observer. And then just a few more days later, it even picks up on secondary characteristics that I expect in a type 1a. In particular, 1As are well known to have this secondary peak in the redder bands that we think is an opacity effect. We're not actually sure yet. And so that's really exciting. It seems like this autoencoder we've introduced has, without any physics, been able to understand how to extract interesting parameters to describe these light curves. And I'm going to use those parameters, which I call my learned latent space, to do lots of fun things like classification or some other things. And we're not necessarily going to dive into the classification component. I will just say that we have done this on real data. We're continually trying it on new data sets as well. Feel free to talk to me about this either after or now. But I really like to take a step back and highlight the fact that we did not necessarily, all these bells and whistles are not for the sake of bells and whistles. We design a machine learning technique that fits our physical needs. In particular, again, semi-supervised because we know that only a small fraction are going to actually have a spectrum, which is the label. The autoencoder allows us to extract nonlinear features are really the big thing. You can ask me about why we expect nonlinear features if you want to. The recurrent neurons, as we said, are able to update our best guess of this latent space as we keep observing. And most importantly, it's physics agnostic. We've done something which can make predictions without knowing what we are looking for. And so now we are going to use this exact same architecture to look for needles, where by needle, I mean what I find to be the most exciting. What is the 1 in 1 million physics that we don't even know about? Well, I'll say astrophysics that we don't even know about that LSST might actually observe. So how do we do that? Basically, we encode every single light curve into this small space that we're already familiar with. It's called the latent space. And then we can imagine doing something like this. For every single supernova, I just take like 2 values in this kind of encoding vector. Maybe one corresponds to mass and one with energy. Not really, they're going to be strange features of the light curve. They're not physical. And I'm going to make a plot like this of every single supernova. The thing I haven't mentioned is that it's a variational autoencoder, which has a few implications, but the one that's important is that the autoencoder is going to try as hard as it can to fit every single supernova into a tight Gaussian distribution. And if it can't do that to you, you must be pretty weird looking. And in particular, we look for those weirdos, which are anomalies, by using something called an isolation forest. An isolation forest is really easy to understand. Basically, I just make a cut in this space. And if I make I'm not very good at it here, but if I make a cut here, I would immediately isolate the 2 guys on the left. However, if I wanted to isolate some of these guys in here, oh goodness, this would take a pretty long time to get them in kind of their own little tile of different cuts. And so what an isolation forest does is the number of cuts it takes to isolate you from the population is inversely related to how anomalous you must be. And this anomaly score has nothing to do with physics. It just has to do with how weird you look to my neural network. And so we actually did this study with simulated data. So we knew the answer for which physics was rare versus not rare. This is a complicated plot, so please, in many ways, take my word for it. This is showing the anomaly score we get from that isolation forest as a cumulative distribution for all the different types of physics we looked at. And the point of this plot is that the weirdos, so the brown and the red in this case, which if I remember correctly, yeah, are one of them's these super luminous guys that we just talked about, super weird. And the other one is actually the other luminosity extreme. It's called intermediate luminosity transients, and I can talk about it if you want. But both of these are highlighted as extremely odd to our autoencoder. So the rare physics is in fact highlighted as weird. And yeah, okay. And then the other, at the other extreme are type 1a supernovae, which are the most common thing we see in the sky by far. They make up about 70% of the sample. And those are at the other end of anomaly scores. They tend to not stand out. Yeah.
Yeah, I was wondering if this distribution of the cumulative distribution functions for the events, it must depend on what you've used to train the model, right?
It does.
You had fewer intermediate luminosity transits, and that's why they're picked up as weirder, right?
So that's exactly, yeah, okay. So, so this is exactly right. So, and I point to this again later, we purposely, well, someone has done all the hard work of injecting these into LSST. So we use something called the plastic simulation here. And it really does represent the observational rates we expect. And so I am just injecting what I expect the universe to give to us. And this is exactly why it works. It knows that the universe likes to give us type 1As. And so it will naturally call them not anomalous. And because the universe does not like to give us superluminous supernovae, it will naturally call them anomalous. Yeah. Yeah.
You make a point of saying that a lot of the way that you're going about, or the way your neural network picks out parameters to classify these things as not physical, right?
Yeah, I do make a point. Yeah.
Okay, so you're saying that, but I wonder, is that very strictly speaking, meaning it cannot be physical, or is there just no reason?
Oh, yeah.
Or so assume it's physical, like it can be
Yeah.
mass times energy to like the 20th divided by.
Yeah. I love this question so much. People are working, okay, I'm actually gonna a little bit later talk about how you can help that problem of exactly what you're speaking. One could definitely imagine that I could write down a symbolic formula to get the physical properties out. I haven't tried that. So that's partially why I'm claiming that. And in particular, because this is variational versus the, just dropping that adjective, the not variational version. One thing that we've at least done well is that we are trying our best to have a continuous latent space, and we assume our physics is continuous. So that is one thing that would help us in the problem of trying to convert this into physical properties. Yeah, so one could definitely do that. I'm specifically not claiming that though.
There's a question on Zoom.
Yeah.
Alex, do you want to go ahead and ask your question on Zoom?
Yeah, hi, Ashley. I was wondering if you now have this latent space of all of your features where you have a sense for what region of this multidimensional space is comprised of weird light curves and what region of space is comprised of common objects. Could you then oversample in the space and then decode back into light curves of objects you think might be really strange, try and get some understanding of what they might look like?
Yeah, that's a really fun idea. I have not done that. One could definitely do that. In our case, instead, we just asked the question, what are the things that stood out? But yeah, you could totally do this.
Thanks.
Yeah. Okay. Oh, go ahead. Yeah.
Yeah, maybe similar to this question. So when you in the latent space, I guess it's a multivariant Gaussian where the
Yeah.
matrices are right?
Yeah, so we do, this is like the really vanilla thing in variational autoencoders where you make it you can even tell it's a like literally diagonal normal. The standard deviation is 1. Yeah.
So what I was thinking is that for every feature, if you take like a 3 sigma deviation and you do what maybe you get a 1000 sigma.
Yeah, that's also a really fun idea. That does build on what Alex says, where the question idea was you could specifically kind of go along eigenvectors and like look at what's happening there. That could be super fun. Yeah. Cool. Okay. So let's move on kind of rapidly. Sorry. I like to zoom into one example of how exactly this kind of anomaly detection system may work in practice. So this is one of our examples, for example, the superluminous supernova. I know I just told you that it's not going to be a needle of LSST, but in our sample, it's one of the most rare physics that are actually simulated. So we're using it as the example. So this is from, again, the plastic simulation. So I know what type it is. I don't like the way I do this, but so what happens is that as I see more and more points of this light curve, the different, it gets encoded every time we have a new observation into my latent space. And then I can watch kind of those latent features change over time. And the color in this plot is actually telling you at what point it went from not interesting to the top 1% of my anomaly scores. So the time in which we would actually trigger on this event. And this is showing you a different representation where the purpleness shows going over as we get more observations. And you can kind of get an intuitive sense of what's happening. Oh, it's walking out of that distribution where the cloud of other supernovae are. And what's really exciting here is that we find that we're able to trigger on these rare events way before peak light, which may be meaningless to non-observational transient people. But basically, the most exciting physics, you definitely want to try to get before peak, because once it's brightest, as a practical level, it's the cheapest time to get spectroscopy, but also because a lot of interesting physics happens before the peak of the light curve that we're seeing. Lots of transient physics can happen. So this is really exciting. We can actually seemingly activate on rare physics in real time before it's quote unquote too late. Okay, in the last few minutes, this is maybe a little rapid fire. I think now I want to, again, think about the broader implication of these methodologies and really kind of make a pitch to the wonderful scientists here at CCA that there are really interesting connections between the physics that we want to understand and the tool sets we're designing. If you're interested in having physics-informed machine learning, this is really one of the fields to do it in. And that's what I've been thinking a lot about, is how do we inform the physics about these domain-specific prior knowledge that sits in our heads. And in particular, I like to think about in terms of this question, where can I put my physics in these models? And I've come up with this inverted pyramid scheme to do so. And I'm not the only one, actually. I was upset. I thought of this and I thought it was very clever, and then realized there's this really wonderful recent review on, I think it's called Physics Informed Machine Learning as well, that has a similar structure. But basically, I'm going to step through how I have been thinking about injecting this physics into three components: the model itself, the data that we're playing with, and the cost function or the objective function that we're trying to optimize. So first, one of the easiest ways to do this is through the data itself. And this is actually exactly the question that was brought up, which is, oh, well, is your anomaly detection learning that something isn't interesting because it sees it and different ratios? The answer is yes. We 100% want to use that knowledge. We know that physics doesn't come equally. This is just a simple histogram of the different types of supernovae we see at different redshifts. And we 100% want to capitalize on that information that we have by implicitly biasing our data with a strong prior that matches reality. There's other ways you can do this too. A very different way of looking at this is that our data has symmetries within it that we know can still conserve the physical quantities. The silliest example is if I turn a picture of a galaxy, it's the same galaxy. So there's a rotational symmetry in those images. But there are more complex symmetries that also exist. So I highlight one paper by Kyle Boone, which is to think about in supernovae, I know that the amount of dust that's in the Milky Way that's in front of my supernova has nothing to do with the supernova. So my latent space encoding had better be independent of that dust. And things like the redshift, the time dilation effects we get, or the K corrections we get, maybe I really want my latent space to not know about that because I only care about the physics. A different place where we can inject our physics that I've really been actively thinking about is inside this cost function or the objective function or the loss function, whatever like word you want to use. It's the thing that I'm actually optimizing when I'm telling my neural net it's done a good job versus a bad job. And again, I've showed you this cartoon hierarchical graph of how we classify different supernovae. And this can, in principle, be translated into a hierarchical cost function where instead of giving it a thumbs up for getting type 2n, well, let's start with this, type 2p correct. Well, I can give it a thumbs half up for getting, for just saying, I think it has hydrogen. I don't know anything else about it. Or I think it totally does not have hydrogen or helium. I otherwise don't know anything about it. And that graph structure, the way you would go about doing this cleverly is just making sure that you can write down the graph, write down the adjacency matrix, and actually build up a conditional probabilistic type of loss function. This is a very complicated slide, I'm sorry. This is a really different world now, but this is a different way in which we thought about, it's not quite an autoencoder, but we were building a latent space for a different time domain problem. In this case, we were interested in the light curves of active galactic nuclei. So those are these supermassive black holes that are actively accreting. And there's lots of theories that you can use the light curves alone, like the ones we'll see in LSST, to get a guess at the underlying interesting physical parameters. So things like the black hole mass of that AGN. And this is work that was done while I was here as a postdoc with Dr. now Jiwon Park, she just defended, who was a visiting pre-doc here. And what was so interesting about this project, in addition to the fun implications, is the fact that actually when we were building this latent space, we specifically rewarded it for simultaneously doing a reconstruction of the light curve, just like an autoencoder would, but also to have probabilistic predictions of these physical parameters. So by having this regularization function, we were actually able to, exactly what someone asked, interpret our latent space directly, which was really fun. And I also want to highlight the fact that this work, beyond supernovae, it will be just absolutely essential in LSST when it observes something like between 20 and 80 million AGN over 10 years. And then I also want to highlight another project that we did here while I was at CCA with another really wonderful pre-doc, Leon Chan, who is now on the graduate school market, where we looked at the kind of the last part of this triangle. We actually said, what if the model itself enforced these interesting symmetries that we know about? So for example, what if I forced the encoding of a galaxy who's flipped in any direction to always look the same, not by showing it different images of flipped galaxies, but by saying you have to enforce rotational symmetries. We did a kind of a baby version of this by looking at a series of periodic variable stars detected with the Zwicky transient facility. And the way we enforced this in our neural network is just by making sure that we always showed it light curves which had periodic boundary conditions, therefore enforcing said boundary conditions. And we actually used this model again to do an anomaly detection search, not with supernovae, but with these variable stars from ZTF. And what's fun is that I'm not a stars person, but we did find some really weird stars. And this is, again, there's authors in this room. What was really fun is that we actually, we notably seem to highlight some really weird group of stars that seem to be evolved and dusty, and then periodic with higher order modes, red giants. And so this is, although these were found purely as ZTF data, this is now basically the HR diagram from Gaia data that shows that the majority of these things that looked weird in ZTF also stick out in this kind of evolved stellar space in Gaia. And again, what's exciting is that these types of methods can easily be extended to the about 100 million stars that will be observed over 10 years with LSST. So that was a whirlwind, apologies. But the whole point here, again, I'm going back to these kind of questions that there are truly some really, really fun questions which bring together interesting physics that we can finally uncover with LSST and really fun interpretability problems that we can start to solve in machine learning itself. And I think that time domain astrophysics has really highlighted how much of a perfect union this can be. And so with that, I will say thank you so much, and I will take questions.
Okay, thank you, Ashley.
Yeah.
We have a couple minutes for questions. So we have some on Zoom, so we'll start there. You may have disappeared. Please raise your hand on Zoom if you have a question. Do we have any questions in the room?
Gabby's hands up. Oh, that's...
Hey.
Hi, Gabby.
Okay. I have like a maybe dumb question about the plot where you show the real-time neurons switching to being not anomalous to anomalous.
Yeah.
It's like moving away from distribution.
Yeah.
You actually get even earlier detection using the direction in which it moves, like doing it meta way. Like right now, you can when it's outside, but you can get like the,
I see what you're saying.
Direction. Like
Yeah.
moving away from that. You can predict where it will be, so you can get even earlier detection. Right?
Yeah, that's a really fun question. I didn't here on the paper, I think, but we didn't try that. So we didn't try that, but that's actually a really fun point. Yeah, like you could see what the flow is and then what's going counter to that. Yeah.
So maybe related to the question of Mateo, so how can you really distinguish something that is physical from some systematic effect, let's say in the instrument? Maybe that you have, I don't know, the instrument broke or something, and then you...
Yeah, okay, so the question is, how do you actually identify something that's physically interesting versus other? And so I'm going to answer that in two parts. The first is that there's a whole class of problems called like real bogus classification, and luckily those have been worked on for many years. And so those classifiers are pretty good, thanks to the fact that instrumentalists really try to understand their system. However, we can still get things wrong. And in a lot of studies I'm shown, one of the key issues we have is that we're relying on photometric redshift estimates. And if those are wrong, they can show up in a really weird way. We did luckily find, I didn't show this plot, but we did run a diagnostic of like, is that what's causing things to look weird? And for the ones where that is the issue, we often, for whatever reason, trigger on them as being weird looking after they've reached peak. And so luckily there are events where we wouldn't probably have used our very scarce resources to follow them up anyways. Yeah.
More questions? I have one. So you started by talking about the flood of data from LSST and how we have to prepare, and you showed a lot of work in that direction. So would you say, are you satisfied with, like, do you feel like you have the tools now, or just needs incremental progress, or
no? It's very bad. We need a lot of work. Like, there's so much work to do in this space. A lot of it, I think, can really benefit from this last section of my talk of, okay, how can we actually start building the physics into these models? Yeah, just in terms of like our classification accuracies aren't great. I just mentioned photometric redshifts. Those aren't quite where they need to be for us to get accurate measurements. We have, on a logistical level, no idea how we're going to actually figure out which ones to trigger spectra on as a community. That's like a human problem. There's so much work to be done. Yeah.
John, on Zoom.
Yeah, so this is, oh, hi, Ashley, amazing talk. So this is related to this human question, right? So I guess your classification gets better over time for any given transient. So are you worried that you might devote all of your follow-up resources to only looking at things that have a high anomaly score later on, and you miss some interesting stuff happening early on that you might just have to like take a leap of faith and guess at random that and hope this one will be interesting.
Yeah, that's a really interesting question. And again, like you said too, it's human. There are lots of strategies people have to mitigate, let's say, there's so many problems in this question, sorry. People do have strategies of how do we mitigate biases in some of these classifications. Like if we only follow up weird transients, then we bias our training set to have heavily labeled set of objects that are very rare. I am in the camp where I think 1 in a million physics should be triggered on, because this is like our chance to get it. As long as there aren't too many people like me, we're okay. That's the best I can say.
So related to your answer just now, so you have this extreme selection bias, right? Looking for rare events.
Yeah.
Have you thought about how to do population estimates for how your dynamical trigger affects population estimates? Can you do them?
So that's again a really interesting question that really has not been touched. There are very few population level studies of supernovae, and this is a huge question if we want to understand how progenitor gets to supernova type, like how that connection actually works. It's really open-ended how those biases are going to get baked in. Yeah.
Okay, I think we have time for one more question from Alex on Zoom.
Hi, great talk, Ashley. This is kind of related to the, there was a question about really fast, really rare events and when you decide they're interesting enough to trigger on. In this slide here, you're showing an event becoming more anomalous with the time relative to maximum luminosity. I was wondering if you looked for rare events in the plastic dataset with much smaller timescales to maximum luminosity and what they do in this plot all the way to the right.
Yeah. So it's kind of hard to answer that question. Just so everyone knows, there's kind of a baked in correlation. If you're brighter, you tend to last longer. So typically the really fast evolving things are also dim. Alex, I'm sure knows this, there's one caveat, which are the cow-like events that you can ask me about after, which are not actually in plastic. So I haven't tried this on those types of events. So in our case, kind of the most quickly evolving event would be kilonovae, which you comically can't really see because there's only 2 of them in plastic and they live like here. So they are on the upper anomalous end of things. They're not in the top 1%, likely because, again, Alex knows this, it's hard to find kilonovae, which are really short-lived and really dim in this LSST observing strategy. LSST will very likely have a different strategy to look after kilonovae, which have a LIGO trigger associated with them. And I can tell you about that afterwards if you want to talk about it.
Thank you. Wonderful talk.
Yeah.
Okay. Thanks, Ashley. Please join me in thanking Ashley again.